All right, so this is meant to be your introductory set of notes for Unit 9. Here we're talking about something that we actually could have started the year with. And we're introducing it now because it's a nice way of backtracking, talking about things that we've already discussed: acceleration, velocity, changes in position, using a new lens, I guess you could say, of describing how and why things move. Instead of looking at it in terms of forces being applied to one another, we could actually look at it in terms of energy. And we didn't start the year with energy because it's a really abstract concept. You can't pick up energy and put it on a balance, or attach wheels to it and measure its rate of change of position like we did with the meter sticks and the stopwatches in the hallway for those little buggies that we started the year with. So I like to hold off on this until we get to the point where we have to transition from Newtonian physics, the older physics that we've been working on for a while, the stuff that Newton helped us explain, to the newer things with electricity and light and sound and the more modern, I don't want to say modern physics, more modern physics, right? Things that aren't 400 years old, things that are, 100 years old. So that's really the idea. We got to start by talking about first what energy is. And that's literally this first vocab term that comes up right here. Energy is a property of matter or radiation. Radiation just being light, right? It doesn't have to be harmful radiation that hurts you or gives you cancer or melts your skin like gamma radiation would. It's visible light. It could be infrared, body heat light that you emit, right? The military for decades has had night vision or infrared goggles, and amphibians and reptiles can see or detect, I don't want to say see, can detect body heat and infrared radiation. So those are totally things that exist out there. Or even your cell phone releases radio waves. They're not harmful. It's just a form of radiation. But the idea is that this energy is an abstract concept that connects both what we've done so far with material stuff, matter, and what we will be doing later on with radiation, which is why I want to talk about it. So that's actually where we're going to start with all of this, is we're going to talk about how energy is responsible for causing motion. And then from that understanding of how energy relates to motion and comparing it to what we've already done, so that, we can look at it and say, this totally checks out. Now we can take that idea and progress to things that we haven't discussed yet. So this is going to bridge our gap in our understanding between things like mass, heat, light, sound, all of the above. And that's the idea behind energy. That's why I like to hold off on it, right? Talk about mass and matter for a while and the things that it can do, and then we transition into the more abstract heat, light, sound, all that good stuff. The first vocab term we're going to come across where we got to really start talking about what's going on here, or I guess you should say the first equation that we're going to come across here is the equation for work. This isn't what you do after school to earn money. This isn't what I'm doing right now. Work is meant to be, in terms of a definition for physics, how things can be done to an object that change or changes the energy that system, really that object has. Now, in physics, we call them systems, as opposed to singular objects, because you could have a car driving down the road with 3 people in it, at which point the system is the car and all 3 people and the cup of coffee that's in the cup holder, and it's everything. I just like to say object because it sounds less pretentious, but really we're just talking about something done to an object by the outside world that changes the amount of energy it has. We'll talk about versions of energy here in a moment, but it's going to increase or decrease that amount of energy that an object has. We're going to go back to that Greek letter delta, right? Change in, and we're going to get there in a second. The equation for work is the force of applied to an object multiplied by the distance that the two of them are traveling, right? So this isn't force plus distance. Force divided by distance is force multiplied by distance. And there are a lot of different ways that we could write out these units, right? It could be a Newton meter, a kilogram meter squared per second squared. Lots of ways that we could write it out or describe it. And instead, scientists decided to name this, like we did a Newton being the unit of force, after another scientist, and we named it after a scientist with the last name of Joules, right? So we refer to the unit of work as a joule. Not the thing that you might vape in the bathroom and you don't think that we know about it here at school, but the scientist from the 1800s, I think it was. Doesn't matter. Anyways, so that was work, right? Work is done on an object to change the amount of energy it has. Specifically, there are multiple kinds of energy, right? We've got kinetic energy. Energy is the energy associated with motion, associated with moving things. And that moving thing could be an object's velocity. It could be light traveling from one place to another, sound traveling from one place to another, heat dissipating or traveling from one place to another, right? Any of those things that can move is a version of kinetic energy. Kinetic energy can be calculated by 1/2 of the object's mass multiplied by the square of the object's velocity. Now, we didn't invent this equation. This is what we've noticed based off of observations. Honestly, it all comes back to a graph. The book does a good way of representing those graphs and showing you that this is indeed a quadratic relationship where the axis, where you find the velocity, wherever you plot it, changes exponentially, right? And so we know it's got to be squared. And this is where we get all of the equations have come from graphs, and we started the year with that. We're not doing it so much now because that would get really redundant, but that's where they all come from. Your units are still going to be mass multiplied by units of velocity, but that velocity got squared. So remember that if you distribute that square, you're going to get a kilogram meter squared per second squared. That should look really familiar. Look at the top of the screen right now. It was the same unit that we came up with when we multiplied a Newton by a meter, or a kilogram meter per second squared multiplied by another meter. And so units of energy, kinetic energy, are still going to be measured in joules. Now, that's not a coincidence, right? There are very few coincidences that I've ever encountered in life, or especially in science, right? So work is measured in joules. Kinetic energy is measured in joules, and that really comes down to the idea of the work-energy theorem. Remember, the definition for work was the ability for you to cause a change in an object's energy, how much energy it has. So if we're talking about kinetic energy, change in kinetic energy, work is equal to how much its velocity increases or decreases by. And if you want to speed the object up, you have to put work in. If you want to slow the object down, you have to do negative work, literally, is what you've got to do. It doesn't have to just be kinetic energy. We're in a moment, as you can tell down here, we're about to talk about potential energy. Work is just equal to the amount that that energy changes by. So it could be potential energy, it could be kinetic energy. If the energy of a system changes, work was done on it. That's the relationship. That's the work-energy theorem, right? This is one of the objectives from the cover page. So as you're going through and reviewing for the exam, make sure when you see the objective, understand the relationship between work and energy. Know that for the energy of a system to change, work had to be done. Doesn't matter if it's kinetic or potential. Speaking of potential energy, right? Potential energy is energy stored due to the position of an object. Now that position could be microscopic or macroscopic. What the heck do I mean by a microscopic position? We could be talking about, sure, the relative position of a baseball above the ground. We'll get to that with gravitational potential energy, the kind that we'll calculate here. But there's also potential energy stored in the chemical bonds inside of molecules, right? The peanut butter and honey sandwich that I had for lunch. I usually have that for lunch. Let's just look at the peanuts and the peanut butter, right? All the energy that I got from eating the peanut butter, my body is burning right now. It takes the peanut butter, it goes into my stomach, it gets digested, broken apart. It's literally ripping apart chemical bonds inside of the peanut butter, and I'm using that energy that was stored in those chemical bonds to do things like talk, wave my hands, write, have a heartbeat, have brain function. All of those are really important things that you kind of need to exist, have to have energy. You get that energy from breaking apart the chemical bonds inside the peanuts. Where did the peanuts get the energy that they had? It doesn't matter how long you want to ask this series of questions or where you want to start, whether or not it's peanut butter, bread, honey, maybe a piece of bacon that you ate for dinner last night. It doesn't matter where you want to start this conversation. All of that goes back to the sun, and it goes back to photosynthesis. That is where we get our energy, right? So if we're talking about the peanut is a plant, and it takes that sunlight It takes carbon dioxide from the atmosphere, water either from the atmosphere or from the ground, and it combines those two, and it makes chemical bonds and takes those small molecules of carbon dioxide and water and builds up really large sugars. Other things, but mostly sugars. And it stores that sunlight, literally sunlight, inside those chemical bonds, and then I ate the peanut, and that's where I got my energy. Right? So that's your chemical potential energy. It is stored energy based on, in this particular case, microscopic positions of those molecules or of those individual atoms. Nuclear potential energy is another really good example of potential energy. We could talk about nuclear power plants. Sure, that's a good example. We could talk about nuclear bombs, right? Hiroshima or Nagasaki, when you rearranged that nucleus and caused fission to occur where it broke into smaller pieces from chemistry last year, there was a lot of energy that was released. Sure, it comes from the quantity and arrangement of protons and neutrons inside the nucleus. The other thing that we could do in talking about nuclear potential energy is just talking about the amount of, if we took uranium-238, and we broke it up into its pieces, it turns into, I think it's like thorium and something else. Doesn't matter. But those individual pieces that it breaks up into, if you were to add all of their mass up, really doesn't equal the mass of the uranium-238 molecule. Or nucleus. It doesn't add up to be what it should have started with, right? Even in the sun, it takes 4 hydrogen atoms and fuses them together to make a helium atom. And normal common sense should say 1 + 1 + 1 + 1 = 4. But in the sun, one hydrogen atom plus 1 hydrogen atom plus 1 hydrogen atom plus 1 hydrogen atom, 1 + 1 + 1 + 1 equals like 3.98. It doesn't equal 4. What happened to that missing mass? It's the sunlight that went into my peanut, right? And so all of that energy is still accounted for. So that's the point, is we're storing that energy either in a nucleus, which could be released through sunlight, or nuclear reactions, right? Bombs or power plants, doesn't matter. There's energy stored in those nuclei. Elastic potential energy is another one, right? You stretch a rubber band, it has the potential to snap back to its original place. You could even talk about springs having this sort of elastic potential energy, but it's all based off of, this is actually a term in physics, elasticity of an object. How would you know the elasticity of an object? Well, go to a physical therapy place or a gym, and you'll see the red colored band and the green colored band and the yellow colored band and the purple colored band that I'm still not allowed to use because I just had surgery, right? They don't want me ripping my bicep back off of the bone that they just fused it to. Ironically enough, it's weird. Anyways, elasticity, right? How elastic that thing is another way of describing potential energy. You can store energy in elastic objects. But the one we're going to primarily use in this class, because we are using energy to look back real quick at what we've already done, is gravitational potential energy. It's based off of your position and how much gravity can influence that position. It is determined by the product. I don't use that word lightly. It is literally multiplication. The product of the object's mass, the strength of the gravitational field, which was a fancy way of describing acceleration due to gravity, the strength of the gravitational field present, and the height above the nearest support surface. Because once your pen falls from your desk 30 centimeters down to your desk, that's the support surface. Gravity's done working on it. Gravity is literally done being able to move that pen until you move it over the edge of the desk, and then gravity can work on it for another measurable amount of distance. And so it has a new measurable amount of potential energy. Notice, units are still joules. It's always going to be joules. Now, there is a more complicated version of your equation for work, and this is actually what pops up on that reading note quiz. The inclusion of this cosine function is actually crucial. The inclusion of this cosine function helps us recognize that sometimes when you apply a force to an object, not all of that force goes towards moving it in the direction you want it to move, or moving it in the direction that it is moving. So you've got to be careful with that. Work can only be done on an object if it changes. This is the second time I've wrote this, so this is definitely a test question. If it changes the energy of the system. If it doesn't change the energy of the system, no work is being done. Kinetic or potential energy, doesn't matter. Work must be done if that energy was changed, or to change that energy, work must be done, I should say. So we can calculate how much work is being done in each of these three examples. Notice the angles change. So the equation is work equals force multiplied by distance multiplied by the cosine of theta. And in this particular case, when we want to calculate this work, I've got 5 newtons of force being applied over 5 meters, and the degree measure between those two angles, those two vectors, the angle measurement between your 5 newtons and your 5 meters is 0. They are both in the same direction. And if you remember your basic trig from algebra, pre-calc, whatever it was that you might be taking or have taken, the cosine of 0 is always 1. So your work being done here is 25 joules worth of work. All of the force you applied was responsible for the displacement that that object had. Notice the middle example. Not all 5 newtons of that work, or of that force, is responsible for the 5 meter change. You've got a horizontal component to that force vector. You have a vertical component to that force vector. Only the horizontal component of this 5 newtons is responsible for moving that block 5 meters to the right. So when we plug that back into our work equation, work is equal to force multiplied by distance multiplied by the cosine of theta. When we plug that back in, you're going to get a very different value. You still have 5 newtons of force. You still have a displacement of 5 meters, sure, but they're now no longer in the same direction. There is an angle between them. Only a fraction of that 5 newtons was responsible for moving this object to the right 5 meters. And so that's going to give you a very different amount of work being done. I think it was 22.7. Yeah, if you round correctly. 22.7 joules of work being done. Again, part of that work was actually done vertically. Now, it didn't move vertically, which means it didn't change the energy of the object, so no work was being done vertically, but part of that force was vertical. And only the horizontal component of that force was responsible for the horizontal motion. That should make sense if you say it out loud enough times. Here, in our last example, I am applying a force downward of 5 newtons, and the box is still moving to the right 5 meters. No time in my life have I ever applied a force downward and something moved to the right as a response. Right? It's just never happened. But mathematically, we can explain why that is. You've got your 5 Newton force that you applied. The box travels a 5 meter distance still, but the cosine of your angle between those two vectors is now 90. Just like the cosine of 0 was always 1, the cosine of 90 is always 0 from your trig. And so you're doing no work. Basically, what this is telling you is that the box might be moving to the right, but it's not moving to the right because of the 5 Newton force you applied to it. It's moving to the right because something else is happening to it. We don't know what it is. It's not represented in this diagram, but your 5 Newton force is not responsible for that motion. Therefore, according to physics, you're not doing any work. And that's all it is. So you got to include that cosine function. More often than not, the angle will be 0. Cosine of 0 is 1, and we can ignore it. But there will be worksheets, obviously, where that angle isn't going to be 0. Only part of our force is going towards doing work on the system. So this is really just a summary of exactly what we just saw in those previous boxes, right? If they are in the same direction, then you're going to have the most amount of possible work being done because the cosine of 0 is 1. If there is some angle between them, you'll get a little bit less work being done on them, right? It was 22.7 as opposed to 25. If we increase that angle, it'll be less. As that angle approaches 90, though, you get closer and closer and closer to having absolutely no work being done. So in scenario number 3, what happened? The net force vector cannot be the cause of the displacement because the net force vector was in the downward direction and the displacement was to the right. Or you could remember that the cosine of 90 is always 0. Last but not least for this, that was the bell, I got to get going. So power is the rate at which work is done. You could change the energy of a system slowly and generate very little power, or change the energy of a system very rapidly and have a lot of power that was produced, right? A rate is just a measurement compared to how time progresses. So it's something divided by time. And so in this case, it's work divided by time. Usually that unit is going to be watts. Units of watts are really, really, really small, so the electric company will bill you in kilowatt hours, technically. But that's it. That's power. So assignment 2 is really just practicing each one of those equations that we discussed in those notes, and that's where we left you guys for this week. We'll pick up Monday or Friday, depending on whether or not you're an A day or a B day, with notes on machines. That's about it.